Hi girls, today we're going to start with lesson 2 according to Hagen. In this lesson, applications of induced currents, we will discuss first Lenz's law. This is a segment in the book about Lenz's law. You can pause the video and read it carefully. Now let's consider this case. We have a segment of wire and it's moving downwards inside a magnetic field directed into the page. So this is the wire. I'm moving it downwards and we have a magnetic field directed into the page, as you can see, or into the screen. Now, when we move this wire down, we have induced a current inside the wire. According to Faraday, if we have a wire moving in a magnetic field, an induced current will be formed, and the direction of the induced current can be found using the right-hand rule. The thumb will be down in the direction of the velocity. The four fingers will be into the page in the direction of the magnetic field B. The palm of my hand will show me the direction of the current. So here, the palm of my hand will be towards the right, which is the direction of the current in the segment of the wire that is moving. Now we have a current carrying wire inside the magnetic field. And just like we learned in term 2, if we have a current carrying wire inside a magnetic field, it will be subjected to a magnetic force. And the direction of that force can be found using the right-hand rule. You'll put your thumb in the direction of the current. You'll put your four fingers in the direction of the magnetic field, so into the page. So these are your nails. Oh, 1 minute. So I towards the direction of the current, your four fingers, the direction of the magnetic field, which is inside. You'll see that the palm of your hand will be directed upwards. So the direction of the applied force is going to be upwards. So the current carrying wire is affected by a force up or opposite to the direction of motion. That's why it's a bit difficult to move the wire in a magnetic field, because it will always be subjected to a magnetic force opposite in direction to that of motion. Now, if the magnetic field inside the loop increases when we drag this segment of the wire down, the number of magnetic field lines inside the loop will increase. If the magnetic field inside the loop increases, a current is induced according to Faraday, and this current induces its own magnetic field, and this magnetic field is going to be opposite to the original one. So عند زيادة المجال المغناطيسي خلال الملف يتولد تيار مستحث يولد مجال مغناطيسي معاكس للمجال الأصلي. So المجال الأصلي ازداد، تولد مجال مغناطيسي معاكس للمجال الأصلي. If the magnetic field inside the loop decreases, فمثلا if we move this segment of wire upwards, the number of magnetic field lines inside the loop of wire shown in blue is going to decrease. So if the magnetic field inside the loop decreases, a current is induced, and this current will induce its own magnetic field. And this new magnetic field will be in the same direction as the original one. So عند نقصان المجال المغناطيسي خلال الملف، نقصان المجال المغناطيسي خلال الملف يتولد تيار مستحث، وهذا التيار يولد مجال مغناطيسي آخر في نفس اتجاه المجال الأصلي. So المجال المغناطيسي الأصلي كان عم بينقص. المجال المغناطيسي المستحث الجديد راح يكون في نفس اتجاه المجال المغناطيسي الأصلي، يحاول يزيده مرة ثانية. يعني هون كان عم بيزداد المجال المغناطيسي الجديد، كان يحاول يقلله. هون لما صار ينقص المجال المغناطيسي المستحث الجديد، صار يحاول يزيده عن طريق إنه يكون في نفس الاتجاه. So you can see that Lenz's law states that the magnetic field produced by an induced current is in the direction that opposes the change in the original field. يكون اتجاه المجال المتولد من التيار المستحث بحيث يعاكس التغير في المجال المسبب له. فمثلا إذا ازداد المجال الأصلي اللي لونه أخضر، المجال الجديد اللي لونه زهري بيحاول يقلله مرة ثانية، فبيكون في عكس اتجاهه، لأنه يعني لما يكون في عكس اتجاهه بيقلل من قيمته. لكن إذا قل المجال الأصلي اللي لونه أخضر، إذا قل مقداره، المجال الجديد المتولد من التيار المستحث راح يحاول يزيده مرة ثانية، فبيكون معاه في نفس الاتجاه. أوكي، هون بتكون شوي أوضح الصورة. هون عنا مغناطيس، هون شوي بس خلينا نظبط. Let's explain it using a simpler method. Here we have a coil, and this coil is connected in a circuit with an ammeter. And here we have a magnet, and around this magnet we have magnetic field lines. Now when we approach the magnet, the amount of magnetic field lines cutting the coil increases. The magnetic field inside the coil increases. And because of this increase, a current will be induced in the wire that induces another magnetic field that would be in the opposite direction of the original one. So what happens here is repulsion. So if we bring the magnet in the coil or towards the coil, the magnetic field inside the coil will increase. This will induce a current. A current is induced that will induce another magnetic field, and this magnetic field will be opposite in direction to the original one. So the original one was directed like this. The induced one is going to be in the opposite direction. See, to be opposite in direction to the original one. So we will have repulsion force between the coil and the magnet. Now what repels north? Another north pole. So we will have north pole on this side of the coil, and we will have south pole on the other side of the coil. And according to the right-hand rule, we're going to put the thumb in the direction of the north pole, and your forefingers will coil like this. If you do this with me, this way we can find the direction of the induced current. So because you can see the tip of your fingers, the direction of the current will be down. It will be down from the side that you can see from the coil. If you move with the wire, you can see that the current will go like this into the ammeter and up from the other side, and so on. The coil repels the magnet because we have like poles. You can see it clearly here from this picture. We bring the magnet towards the coil. Here we are bringing the north pole closer, so we will have repulsion force. Another north pole will be created on the nearest side of the coil, and hence a south pole will be created on the opposite side. According to the right-hand rule, you can find the direction of the induced current in the coil. You can see here it will be towards down like this, and into the ammeter and out. Now, if we bring the magnet out, you can see that we have a traction force between the coil and the magnet. That's because when we bring the magnet out or away from the coil, the magnetic field inside the loop, inside the coil, will decrease. A current is induced because of this change, and this current induces another magnetic field that would try to increase the original one again by being in the same direction of the original field. So when we bring the magnet away from the coil, we will have attraction force. So we will have a magnetic field, an induced magnetic field in the same direction of the original one. So here we are removing the north pole. A south pole would be created on the nearest side of the coil to try to attract it back towards it. That means that the other side would be north. So you can see that the direction of the induced magnetic field is in the same direction as the original magnetic field. That's because it's trying to increase it again. It is trying to increase the original magnetic field. Using the right hand rule, you put the thumb in the direction of the North Pole. The four fingers will show you the direction of the current. Now, if you can't see the tip of your fingers, that means that the current is going up like this. You can draw like really long arrows on your fingers before you go to the exam and use it to find the direction of the current. So the current is going up from the side that you can see and down from the other side that you cannot see. So the coil attracts the magnet. Lenz's law is used to find the direction of which of the following? It is used to find the direction of the induced magnetic field and induced current. Remember, if the original magnetic field is decreasing, the direction of the induced magnetic field will be in the same as the original one. But if the original magnetic field is increasing, then the induced magnetic field will be opposite to it, to try to decrease it again. Let's take some examples. Here we have the North Pole on the side that's near the coil. When we remove the North Pole, we will have attraction force. Remember, when we remove the magnet away, we will have attraction force. What will attract the north? Will attract the north is the south pole. So we will have a south pole here and another north pole in the farthest side. So the direction of the magnetic field will be like this, out of north and into south, like this. But inside, it will be from south to north. So it would be in the same direction as the original one. What about the direction of the current? We're going to use the right hand rule. We're going to put the thumb in the direction of the North Pole. The four fingers will be in the direction of the current. So from the side that you can see from the coil here, the current will be going down, down, like this. You can continue with the wire. You can see that the current is flowing from B to A. Another example, here we are approaching north. This coil will repel it because magnet in, repulsion. What repels north? Repels north, north. So here we'll have a north-south, and on the far side we will have a south or a south pole. If you want to find the direction, of course, the direction of the magnetic field here would be opposite to that of the original one. To try to decrease it, the direction of the current will be found using the right hand rule. Going to put the thumb in the direction of the North Pole. So the North Pole here, going to put the thumb in the same direction as the north. You can see that the current from the side that you can see from the coil is going to be upwards like this. And from the side, the other side, the one that you can't see, it will be down. Continue with the wire. You can see here up, like this. Here it's going to go up, and then from the side that you cannot see down, like this. So the current will be going from A to B. Here, magnet in, repulsion. What repels south? Another south. So we will have south pole here and another north pole on the far side. The magnetic field will be in the same direction as the original one, because here it will be in the opposite direction of the original one. So south like this, and north like this. And here it would be going like this. Out of south into north. So it would be in the opposite direction of the original one. How about the direction of the current? Using the right hand rule, we'll put the thumb in the direction of the North Pole. The four fingers will show you the direction of the current, which is down. Using the side that you can see from the wire, you can see it's still down. B to A, and then up from the side that you cannot see. Here, magnet out, we have attraction. What attracts south? Well, north attracts south. So we'll have north pole on the nearest side and a south pole on the far side. So the magnetic field will be in the same direction as the original one. See, this is the direction of the induced, and this is the direction of the original one. They are in the same direction, out of north into south. How about the direction of the current? Use the right hand rule. You put the thumb in the direction of the north. You can't see your four fingers. That means from the side that you can't see, you can see we have the current up, and from the side that you cannot see, the current is flowing down. So the current flows from A to B. We can pause this question and answer correctly. What are the poles induced on a solenoid? Here we have magnet in, so we'll have repulsion. South, what repels south? South. From the far side, we will have north. So X is south and Y is north. Specify the direction of the induced current. What is the name of the rule you used? We're going to use the right hand rule to find the direction of the current. We're going to put the thumb in the direction of the North Pole. The four fingers will show you the direction of the current. So it will be down. The tips of your fingers are the arrows. They'll be going down like this. From the side that you can see here, you can see that the current goes down from B to A and up again from the other side. So it will be from B to A. What happens to the deflection of the galvanometer needle in the following cases? Now this galvanometer, it measures the current. So when the current increases, the deflection of the needle decreases. And if the current increases, the deflection increases as well. So the deflection of the needle is an indicator of how much current we have in the circuit. The more current, the more deflection. If we move the magnet quicker, we will have a higher induced EMF, because the induced EMF depends on B, L, and V. If the speed increases, the EMF increases. And since I equals to EMF over R, when the EMF increases, the current increases as well. So here it increases. Putting an iron core inside the solenoid makes it a stronger electromagnet, and hence it will increase the induced current. What is the direction of the current when the magnet is pulled away? Well, because we pull the magnet away, we will have attraction force, and hence you will have a north pole here and a south pole here. Then if you put the thumb in the direction of the new north pole, the current will reverse direction. You can see that now the current is going upwards. So we can say that the direction of the current reverses. It becomes up. Or from A to B, opposite to that when we approached the magnet. What is the type of magnetic pole at B? I'm gonna let you stop the video here and try to solve the question by yourself. This one as well.